Hello everybody, my name is Stephen Jin and I'm with the Logisim Calculator group for CST337 Computer Architecture with Professor Jonathan Chu. So we decided to do a calculator for our group in Logisim, which is a utility that uses logic gates. And as you can see, we'll go ahead and get started with the slide that you see here in front of you. This is an 8-bit adder. It can add up any two values, provided the result is fewer than 8 binary digits. In this case, values A and B, which you see at the top there, are added and output to a sum. Now each gate that you see there, the little D shapes and the triangular shaped gates, each gate is represented in reality by a transistor circuit. As you can see, again, we'll go ahead and mention the D shape is an AND gate, and it will output current if and only if both inputs are providing a current, or on, if you will. And as you can see, the triangular OR gate there is the OR gate, which means it will output a current if at least one input has current. I'm sorry. As we move forward, we see the mouse is moving around there, pointing out the sum and the inputs there at the top, values A and B, and we'll go ahead and show where the mouse will go ahead and hover over the AND gate and the OR gate, as well as the exclusive OR, which is the triangle with the extra little line behind it there. As you can see there, we're pointing out the AND gates, OR gates, as well as the exclusive OR gates. And we'll go ahead and move on to the next slide here. As you can see, the highlighted section you see before you is your basic adder, from which all electronic constructs for performing arithmetic logic are derived. It's known as the full adder, and is able to add on bits of information, as well as take on a carry-in value and output a carry-out value. This can perform subtraction using 2's complement numbering system. It can also perform multiplication and division by recursively adding or subtracting. We'll go ahead and move on to the next slide here. There we go. This is an 8-bit flip-flop. You can keep track of previous circuit states up to 8 bits, and then retrieve that information based on a signal. And often the signal comes in the form of a clock in an actual computer system. We'll go ahead and move on to the next slide. The highlighted section, or the section you see in front of you here, is a D flip-flop. It is one of the basic memory constructs that allows the computer to remember data. It can remember one bit of information, which can be later be retrieved by linking these basic units together to form complex chains that can remember many trillions of bits. We'll go on and move on to the next slide here. This is a 4-bit, 32-bit calculator that can be represented in Logisim. Each module represents a system of logic gates, in addition to there being logic gates in the diagram itself. The calculator takes and stores input, records an operation, takes the second input, and performs the desired calculation. This right here is the renderer, which manages output. The display itself is actually a set of logic gates, so in order to get the display to show numbers, a complicated system of logic must be implemented. Fortunately, the circuit is available in the Logisim library. So as you can see here, this is in the Logisim library. So we'll move on to the next slide here. This is just the basic display. It takes in 32 bits of information and stores it, and as you can see, each one of these registers here is 32 bits, And as you can see here, where I'm pointing at, this is 32 bits here, and as long as it's below 8 bits, as you can see 0, 1, 1, 1 is equal to 7. So we'll move on to the next slide here. These are the arithmetic logic units. This is the ALU. So this highlighted section here where the red box is, and as you can see, it's got addition, subtraction, multiplication, division here. So your basic addition, subtraction. So we'll move on to the next slide. These are the registers. They're basically temporary memory spaces for holding the numbers used in the calculation. They're a type of flip-flop which can hold 32-bit values. So each register here holds 32, and we'll move on to the next slide. This is the cache, which holds the result, and there are more. These are again more flip-flop modules, and they hold the result. So if the user desires, calculations on the result can be performed. And so with that, I'll thank you for your time. Oh, I'm sorry. Guess not. So these, well, and with that, ladies and gentlemen, my apologies, but so we're running out of time. Thank you, and bye-bye.